Good. So now we're gonna step into our second invited talk. Jürgen Schmidhuber. He's a very well-known eminence in this field. He has been, since he's 15, dreaming about creating an AI that will be smarter than himself and then retire. We're still all in the process of trying to retire, but his lab has definitely paved the road towards that with very, very solid contributions in, for example, the neural networks. LSTMs came out of his lab and are progressively used in the field. And he's very well known also in more theoretical aspects like the formal theory of creativity and fun. And yeah, like today we'll be hearing about hierarchical reinforcement learning with gradient-based subgoal generator, asymptotically optimal incremental problem solvers, power play, and various methods.
Thank you so much, Carlos. So to me, the LSTM and things like that were only just always byproducts of our true goal, namely to build a general problem solver that learns without a teacher in arbitrary environments, partially observable environments, general reinforcement learning basically. And that's what I'm going to talk about today. I will also say more than I intend to say about power play, which is a system which invents its own goals all the time and is trying to find easy goals that it couldn't solve yet before, and a lot to do with what David Silver just said a few minutes ago. Let me first start, this is my name and how to pronounce my name, by the way. Let me first start with something that is still relevant today, although it happened a long time ago. Lots of papers today have now these reinforcement learning machines that also have an extra input which says, what is my goal? And here's this paper from 1990 where you had a recurrent network or something else, your favorite reinforcement learner, and it gets two extra inputs. It gets a start and a goal. Now I'm so sorry that these words are not in English but in German, because why? Because yesterday I was informed that I'm going to give a talk today and I wasn't able to rewrite all of that. But basically you have a general reinforcement learner and it gets a start and a goal at a constant input, and then it produces output sequences and is controlling an agent and environment. It gets time varying inputs from the environment, of course, and it's trying to maximize the reward on the way to the goal. The goal can be self-invented or previously observed or something. Then you have a second module, which is this thing down here, which is called an evaluator. The evaluator also gets a start input and a goal input, and then out comes an evaluation. And based on previous experience, it has learned to predict the costs of going from start to goal. Maybe it's not possible, then you can have 0, maybe as an output, or maybe you get high reward on the way, then you have a sum of 1 or whatever. Then you have a final system, which is the subgoal generator, the recurrent subgoal generator, which also gets as an input a start and a goal. And it's trying to find a good subgoal sequence. So now it wants to generate a sequence of abstract subgoals, such that it goes first from A to B, then to C, and so on, until it finally has solved the goal. Now, what does this recurrent subgoal generator do? It learns through gradient descent, because everything is set up such that it's differentiable. So there, a subgoal comes out, and it goes into the evaluator. The evaluator says, how much does it cost to do that? Maybe it's really hard to do it, or maybe it's really easy to do that. Then there is the subgoal, which is fed back to the input of the subgoal generator, such that it becomes the new start. Because suppose you have reached this new subgoal, now it's the start of the next remaining sequence of subgoals. And then you can probably see how you can generate a sequence of subgoals like this. And then you unfold the whole thing in time that looks like this, and you train it by backpropagation through time, and you have these copies of the evaluator to evaluate all these subgoals that were invented by the recurrent subgoal generator. And you can do end-to-end differentiation then to find a good subgoal sequence. Some of these things are now widely used, especially recurrent networks or other reinforcement learners that have extra goal inputs, but the subgoal the arriving procedure, I think it's not widely used yet, although it might be promising in quite a few applications. This is an old thing from 1982. We had a series of papers on that, where it learns a bunch of subgoals on the way to a goal. Now, another useful concept of back then, which is also widely used, and I'm trying to limit myself only to things that are useful today, still today, is this idea of compressing one teacher network into a student network. So maybe your teacher network has learned something, a sequence of actions or some sequential behavior that your student network doesn't know yet. Maybe your student network knows other things. Then you want to distill, as it is sometimes called today, but we call it collapsing or compressing. It is learning to imitate the teacher such that it can add something to its repertoire. So before it could do n different things, and now something is coming from the teacher network, which has learned something that the student network didn't know, and it can then use plain gradient descent, and we know how to do that, to squeeze in this additional behavior. And of course it's going to be related then through the other things that the recurrent network already knows. Now back then I didn't call that the student and the teacher, I called it the chunker and the automatizer. So the chunker was a system that tried to learn to find high-level structure in long sequences of data, and there were at least two networks. One was just trying to predict the next thing, given the past, so a standard recurrent network, and then whenever it was able to predict the next thing, then of course this means compression, because whatever you can predict, you don't have to store extra, and then only the unpredictable stuff conveys really information, and that is sent to this chunker network, which is operating on the slower time scale on the higher level, and then it's learning to discover regularities that the lower level network was not able to see. Now it's learning something that the lower guy wasn't able to see. Now we would love to not have this hierarchy of sequence compressing networks where every network is coming up with an even more compact description of the sequence. No, we would like to have a compact representation of everything in one single network. And that's why this thing is now collapsing. The chunker is suddenly becoming, or the behavior of the chunker is suddenly becoming the target, the additional target of the automatizer, which is also retrained on its old things, such that it can learn to absorb this new skill, if you will, into itself. So this is also something that is widely used at the moment in many applications. Now, because David said so much about self-generated goals, this is the essence of power play. And I noticed that quite a few people don't know this power play thing yet, but I think it's a rather fundamental way of solving reinforcement learning tasks. And so you have a bunch of external reward functions that tell your robot what to do and what to achieve, and which are the basic survival goals, and you have to go to the charging station 3 times a day without bumping against the painful obstacles which lead to pain signals through the pain sensors and stuff. So that's the teacher given or the user given or the external goal, but then there are these additional self-invented goals. And power play is really about using a universal task description language which allows you to specify arbitrary tasks, arbitrary reward functions, anything that is computable. And like in the old systems of the 90s, you insert this task description as an extra input. This is what I currently have to do. And then you are trying to find a modification of your current problem solver, which is going to become a more and more general problem solver over time. You're trying to find a modification of the current problem solver such that the new task is being solved through that modification, and the previous problem solver before that couldn't do it, so it's really learning something new. It breaks the generalization ability of the previous problem solver, and the previous problem solver has to be retrained on all the previous skills such that it doesn't forget. So that's what you can do again with this compression mechanism that I just mentioned. So all the time, the system, the power play system, is motivated to invent a new task, and it sounds crazy in a sense because suddenly you have even a larger search space. You are not only given these user-defined tasks, and then you have to search the space of possible solution candidates until you find a solution. No, now you have an even broader space, which is also the set of all possible tasks, maybe of all computable tasks. However, the additional freedom is that the system can choose a really, really simple task. You know, like, as what David said, predict the next pixel or something. Anything. And of course, in the beginning, it likes to invent stuff that is easy to add to the repertoire. So it likes to come up with a new task that is really simple and can easily be absorbed by the existing system, such that it becomes a slightly more general problem solver, and then it learns something that it didn't know so far, and it adds always new skills, to computable skills to the repertoire of existing skills. Power play. Of course, sometimes you force it to do something that you want to do, which is get external reward by solving my particular problem. Here is a simplified application of this power play principle, where there's a really little robot that was 2015, which has learned to invent its own goals, inventing sub-goals by playing with objects and letting them and learning skills that lead to certain states which were interesting at some point in the past of the robot, but it didn't know yet what was going to happen if I do that and that. And it likes to pick the easy skills. In that case, the compression technique that was used and applied to raw vision, so now because computers are so much faster than back then, 25 years ago, when they were about 100,000 times slower than today, now we can do interesting stuff with robots and so on. And then this particular compression mechanism was based on slow feature analysis, which is one way of identifying structure and sub-goal-worthy things in the environment. Let me, how much more time do I have? 10 more minutes. 10 more minutes. Let me talk about an asymptotically optimal way of learning new skills on top of others. And here, for the moment, forget about the power play thing, just assume that there is a skill or a task sequence which is externally given. So you can combine that with the power play thing, but back then, that was around 2004, you had, today people would call it a curriculum. So first solve that, then solve that, and so on. And what you see here is programs written in a universal programming language. Now, I never see a difference between recurrent neural networks and other types of general purpose computers. So lots of our previous work is really sometimes about assembler-like programming languages or other universal languages for computing arbitrary programs. And then in parallel in the same year, a similar system is described where the program is really just the recurrent weight matrix of a recurrent neural network. In both cases, we have a universal substrate, a general purpose computer. In one case, a recurrent neural network. In another case, another type of universal computer and a universal programming language in which we can formulate arbitrary programs. Sometimes this approach has certain advantages over that, but it's not fundamental advantages. Everything that I'm telling you now can also be done with recurrent networks. So here, this OOPS, the optimal order problem solver, is trying to solve one new problem after another, and it's always able to reuse all the previous programs and skills that it learned while solving previous tasks. And it does that in a way that is asymptotically optimal because it's based on Levin's old universal search algorithm, which dates back to 1973, I think. And it's an incremental extension of that algorithm because although this thing is asymptotically optimal, an optimal problem solver that will solve your easily verifiable problem as quickly as the fastest unknown problem for solving that task, except for a multiplicative constant, which is ignored in the old notation of theoretical computer science, but not by us practical computer scientists. So to get this constant factor down, we want to do this incremental learning of one new task after another. And this is what the OOPS does. And at any point, so now a new task is coming in, what does it do? First it tries to solve it like its most recent, most general program that can already solve 10 previous tasks. And if that doesn't work, then it's trying to prolong the previous program in a certain clever way, or it's trying to learn the new thing from scratch. And it is always able to either work by itself and try to solve everything from scratch, or it can spend some extra time and energy on invoking previously found programs, or taking one of the previously found programs and put it on a stack and edit it a little bit and run it on the stack with that small edit, which makes it a different program, but one that is still kind of similar to the old one, such that you can exploit all the algorithmic information that might be there in these different solutions to previous tasks that you could exploit to greatly reduce the search space of your solution finder, such that you can greatly speed up the search. And this was this worked really nice in many applications. Again, universal programming language. This thing was able to define its own names for its own self-defined recursive functions and stuff like that. And then it was trained on a sequence of tasks. First, it learned something about recursion by just solving little context-sensitive language problems. And because it knew something about recursion then, it found it much easier to learn the Tower of Hanoi problem for many, many disks. Maybe you know, if you have Tower of Hanoi, then with n disks, you need at least 2 to the n instructions to solve it. So 30 disks, 1 billion instructions, just sheer runtime of the program. That's why I call it a very deep problem, because you really have to go deep as you're doing the credit assignment. 1 billion steps during runtime. So this was then able to learn that, and because of the prior knowledge that it got from previously learned tasks, it was able to do that 1,000 times faster than doing it from scratch. So instead of 4 years, we had to wait just for a few days back then with the slow computers. We have a little company, Nascence, which is trying to use the fast computers of today to make all of that much more practical. And maybe you saw that just yesterday, the team of Nascence won the Learning to Run competition against 500 opponents. And we are also hiring both the academic lab, the Swiss AI lab, and the company is hiring. Thank you for the moment. Oh, we have time for questions? Okay. But I said everything, so.
Well, I have a question. Like, there's few some architectures that have provided incredible advances in the field of deep learning. Evolution is one. LSTM is another one. LSTM particularly interesting for this flavor of universal compute that it has. And you said in this talk that for you the LSTMs already had everything that a universal computer would need. Do you think that there's changes in architecture that would help the learning? Maybe do you think that it's worth including more hierarchy in the architectures that we train? Or do you think that training an LSTM in the upper grid will already provide the structure to solve more and more complex problems?
The LSTM is very limited. It's a supervised learning machine, and it is doing gradient-based search in program space, and it works really nicely for speech recognition on the smartphone and Facebook translation 4 billion times a day or so. But it's not a general AI or something. It's a universal computer, but you can use it at most as a submodule to build a more general thing. So, for example, if you have a reinforcement learning system, then you can use an LSTM plus other things to predict the future given the past, and to build a model of the world So that is something we also started doing in 1990. You have a recurrent network, and it tries to predict the future given the past, such that the controller of the separate recurrent network, which is really translating the incoming data into actions, can use the model for planning. So back then we did it the stupid way. We just said, okay, let's run the model network into the future and find a good action sequence that leads to a high predicted reward, vector valued reward signals and so on, and then you can train the controller based on the predictions of the model network, and you can do lots of stuff like that. More recently, we have criticized our own approach there because it's really about millisecond by millisecond planning, which is stupid. That's not what you want to do in the real world. You want to do the sub-goals. If you want to go from here to Beijing, you first think about getting a taxi, that's your first sub-goal station, and then go to the airport, and then for 9 hours nothing is going to happen as you're on your way to Beijing, and so on. So this decomposition of future behavior into meaningful chunks, that is something that can be done with smarter methods, and maybe you want to look at the Learning to Think report of 2015, which can use an LSTM as a submodule, but the LSTM is just a prediction machine which can learn to better compress the data, and you need another LSTM-like thing, the controller, which really learns to act based on, and what you can then do is you can accelerate your search for reinforcement learning solutions through the model and the predictions of the model and the internal representations that the model is learning. But it's just a module of a larger system.
I'll just speed up. Thanks for the great talk. You described a system that can solve for a collection of tasks, each task being encoded in the form of code. What are interesting ways to encode tasks with goals? Or to some
Yeah. So what does the power play do? As long as you run it in unsupervised mode, it is trying to figure out the next simplest task that it doesn't know yet. So it's basically searching. Let me see, maybe I have another thing almost open here. It is searching the set of all possible. Yeah, I have it here. Let me make it big. Okay. So it's trying to become a more and more general problem solver, and the way it does it, at a given moment, it has already learned 100 skills. Okay. Now, what should be the 101st skill that it doesn't know yet? And what it does is basically searching all pairs of task descriptions and problem solver modifications. So that's the problem solver can do 100 different things. The 100 different skills interact and reuse partially their own subprograms. Now, what should be the 101st? Well, it should be the easiest to find, but easy to find in the following sense. Through the modification of the problem solver, you can solve the new task, and it's written in a universal task description language, so anything that is computable, any reward function, anything, you can plug in as an extra input, and then it is trying to solve that, and of course, maybe it's going to fail there, but there's a smart way of allocating runtime to lots of different possible tasks, and it wants to add to the repertoire the first task, which it can add, which the previous solver before the modification could not solve yet, and which doesn't damage all the previous 100 skills. And this takes some time. There's some cost involved in checking whether everything is good and retraining on the previous task, and there are smarter ways and not so smart ways of doing that, but whatever it is doing and however it's spending this time, you want to find the simplest thing, the easiest task to add to the repertoire. And all the computational cost is taken into account. Yeah, there are a couple of experiments with Fourier shifting systems and stuff like that. Yes, so it's a very general, natural way of adding new skills to your repertoire. And I would say that what David Silver mentioned is a special case of this.
Good. We might have time for one more quick question. or otherwise we can just enjoy the coffee break, and the posters are already up, and we can start looking at them, and we'll be back with the next invited talk of Peter O'Leary in half an hour.